So today we're going to talk about our quest to mitigate churn at NOS, in which our intervention consists on proactively reaching out to clients and in order to do a personalized engagement to design stronger customer relationships and keep them longer with us. So one of our analytics process consists on identifying which clients are the riskiest ones to leave the company. And we do that by analyzing early signs of dissatisfaction and other potential churn indicators. And by doing so, we want to do target communication in order to address their concerns, provide tailored solutions, and also to offer incentives to enhance their overall experience with our services. However, given budget constraints, we cannot reach our entire client base. So we must prioritize the clients that are not only the riskiest ones, but the clients that we believe we have the biggest impact on. So for today, we're going to talk about why we believe that the causal inference framework could work to optimize market campaigns. We are also going to talk about our journey and learnings to get to our current solution. And finally, to talk about some of our results that we obtain with our deployment in production. So basically, we can summarize our problem in segmentation 1, in which we can create sort of 4 groups of clients. Let's start with the sure things. Sure thing clients could be the clients that we believe that they are currently happy with our services, and if we don't reach them, they are probably going to stay with us either way. So maybe we should not target them with our marketing communications in order to prioritize other clients. Well, the lost causes are the clients that probably it's too late to reach them, and even if we target them with our marketing campaigns, probably is not enough to make them to change their minds. The not disturbed ones, we could see these clients as the clients that they are probably happy with our services, but if we contact them, maybe it could generate a negative impact, the opposite of what we expected with a marketing campaign, so we probably should not disturb them. And last but not least, the persuadable ones, that are the clients that we really want to focus on. There are the clients in which they are probably not satisfied with our services at this moment, but if we contact them, maybe we can make them change their minds, and these are the clients that we want to focus on. Well, so in the end, we are interested in the heterogeneous treatment effect. We want to analyze in which clients we have the biggest impact, and we do that by basically estimating to what would happen if these clients are treated and what would happen if these clients are not treated given their characteristics. So therefore, why should we use a causal inference approach instead of a traditional machine learning one? Well, as a cliche, we are not only interested in correlation and predictions, but we also are interested in studying which are the root causes for the intervention to be successful. That in this case, we want to understand which clients have the best reaction to when they receive a call from us, and the outcome that we are interested in, that is churning. Well, the gold standard practice to analyze causal effects are the randomized control trials, and in which consist on randomizing 2 groups, the treatment group and the control group. And in the end, we want to analyze the difference between those 2 groups for the variable of interest. In this case, we want to analyze if the treatment group has a bigger effect on the fact that they could churn or not, the probability of churn. However, we could face some pitfalls on the way, even in a randomized control trial. We can have some sorts of biases that could bias our estimates, and that's what we're going to talk about now, about some pitfalls that could be in our way. So first, let's talk about confounding. Let's start with a simple example. Let's say we are interested in analyzing the likelihood of rain. Well, If we look at a barometer reading, if the barometer reading is high, we could say that the probability of rain is bigger than if the barometer reading is low. But now let's say that we have the possibility of hacking the barometer, and we hack this barometer to have a higher reading, and we can also hack this barometer to have a lower reading. Well, in this case, as you can imagine, the likelihood of rain, it wouldn't change, because it's not the barometer that has a causal effect on rain, even though they are associated. So, for example, if we control by atmospheric pressure, the barometer doesn't have an effect anymore. Let's talk now about a more complex example. Let's say we are interested in studying lung cancer and the effect of smoking on lung cancer. There are effects, for example, variables that we cannot measure, for example, the genotype of the people being studied. And since they interfere both in lung cancer and also in the likelihood of that person to smoke or being addicted to smoke and so on, well, this could be a factor that could bias our estimates. And the fact that we can have unmeasured confounding, it leads to this problem that we have on the right about endogeneity. Let's talk about an example of a company in which they assign, they randomize an experiment in which they do push notifications to clients, and they are interested to analyze if it increases the probability of an app purchase. All right. The problem we could have, for example, is that, the engineers, they realize that some of these clients, they have older devices, and these devices were not eligible to receive the treatment, the notification. So if the notification is only targeting clients with newer devices, we could, maybe only clients with higher ranges of income are being targeted, and this could probably be a source of bias to our estimates. And that's not what we want. We want the true causal effect of, for example, in this case, the push assignment to probability of app purchase. So now, given this context, João is going to talk about the learnings and what we've been doing to get to our current solution.
So, our first solution was to use meta-learners. Meta-learners are a well-known type of model, and basically they use traditional machine learning models to estimate each separately effect of the causal inference. In this example, we are talking about the learner, which is one of the most easy ones to understand. And basically, what we do is we split the data set in two. So, for instance, in the image below on the right, you have the characteristics of a client given all the clients that were treated. So, T equals 1. And we train a model using that data set only. If we then make the prediction using only that data set, we have the effect, the probability of, in our case, the probability of churn, giving the features of the client for the clients that have treatment that we treat in the past. And we can do the same for another data set, which is the data set created using the clients that we didn't treat in the past. We train a new model, and we have these two predictions independently, and we have to subtract one from the other. This formula is the same as Gabriel mentioned in the previous slide, the heterogeneous treatment effect. And we have to make the difference to have the heterogeneous treatment effect at the end. These kind of problems have the advantage of being very flexible, because you can use whatever the model you want. If you want to have a deep learning model here, you can use it. It is very easy to understand the idea behind it, and however, it has some drawbacks. Mainly, we have less data to train because we are splitting the data set in two. And as well, because we are using less data, there are some behaviors that can be appearing in both groups that can be hard to catch because we are training with less data. And the model cannot learn that patterns. Our next approach was to use causal forests. You already probably know the random forest. The idea here is very similar. The principle is the same, so you have a lot of trees. In this case, they call them causal trees instead. The idea is the same, however, it has some different objective functions. Instead of splitting the branches, for example, trying to maximize the information gain, we try to maximize the treatment effect between the treated and not treated individuals in that group, and the final value of the leaf of the tree is calculated based on the difference between the treatment and not treatment conditions within that leaf. That is needed because of the counterfactual problem, which is the lack of ground truth. This counterfactual problem is the main problem and the main difficulty of the causal inference problems. Let's go back a little bit for a traditional machine learning problem. Imagine our case, if we have a traditional propensity churn model, so a model that is trying to answer the question, what's the probability of this client leaving the company? We can train a model, we can make the inference of that model, and we can wait. Imagine we are trying to predict if the client is churning in the next 30 days. We run the inference, then we wait for 30 days, and we can check if the client leaves the company or not. And we can evaluate the model using that information. So we have like a perfect, let's say, perfect information problem. In the case of counterfactual, in the case of causal modeling, we have the problem, the counterfactual problem. The question that we are trying to answer is what's the gain that we have to have some treatment for that client. In our specific case, what is the gain that we have that call that client in order to reduce the risk of churn of that client? Imagine we train the model, we make the inference, and we have a list of clients with the score. In this case, the score is called heterogeneous treatment effect. And we call, let's say Gabriel is a client of noise, we call Gabriel. We wait 30 days as well, and at the end we see, okay, Gabriel didn't leave the company. At the first, we can think, okay, if Gabriel didn't leave the company, it was a success, right? Kind of a success, because we don't know what had happened to Gabriel if we didn't call him. So basically, making the link with the matrix that Gabriel showed you, we don't know if Gabriel is a persuadable client or is a sure thing. And our goal is to call the maximum persuadable clients. And to address that problem, the counterfactual problem, what we need to do is to group together clients with similar characteristics. And that's what is done in these causal forwards. Imagine you have some client with a mobile plan which is less than 5 gigabytes, the price is less than 7, and from that group of clients, we can calculate directly that we have a 1% gain of calling that client. Because we are making a random trial control, we'll have the assignment of treatment is random, so we'll have both in each one of that leaves, we will have clients from treatment and clients from control. And in that way, you can calculate that 1% with the formula that is below. So we can calculate the probability of that client leaving the company, giving that characteristics. If the client was treated, minus the probability of that client churn if it was not in the control group. So how can we use it in practice? Basically, it's very easy. It's very similar to the scikit-learn package. We are using EconoML, which is a package developed by Microsoft. You just need to import the package. Then you need to define the package, the model. So the arguments are very similar to the random forest. In the feed, you just need to define the x, the y, and the t. We have a new variable here, which is the assignment to treatment. And then you can do the predict, but in this case they call it effect because we are calculating the heterogeneous treatment effect.
So let's talk again about the randomizing experimentation. Well, the perfect compliance would be the perfect scenario in which we randomize the treatment and control groups, and the people that were assigned to each of these groups, they are, for example, the entire treatment group is they are literally treated, and the control group, they are not. But well, sometimes in the real life, let's say, sometimes this doesn't happen, in which then we have the case of imperfect compliance. So, for example, in our case, we have the randomized assignment. So we have the treatment and control groups. But, however, we can have some clients that they were not treated. And we can think that maybe some clients, they are more prone to pick up the phone, to get in touch with us. For example, maybe people that stay at home for more time, they are more likely to pick up the phone and therefore receive the treatment. So this could be a possible source of bias that we have to correct. So like we have in the right graph, we have the problem that we have confounders that can affect not only the outcome of churning or not, but also in the probability of a client to receive the treatment. And that's exactly what we need to correct. So to have unbiased estimate of the treatment effect of calling the client on churn, we reached the instrumental variables estimation. Well, it consists on using a variable that only affects the outcome through the treatment, and it's not related to any other variable in our study. For example, since it's a random assignment, it's not related to any variable, and we control the mechanism of randomization to see which clients are going to be in each group. So we can use this as the way to get the exogenous effect of treatment the client on the outcome. So in the end, we are not only calculating the probability of a client to stay if they are treated, but also we are calculating the probability of that client to receive the treatment, and then we can have an unbiased estimator. So like João said, it's pretty similar to what we have already worked, for example, with scikit-learn or some of these packages. The thing that we have different here, João already introduced us about the T parameter in the model.fit, that is the fact that the client was treated or not, but now we also have the Z variable that it means the instrumental variable, that is the fact that the client was randomly assigned to be in the treatment or in the control group, and therefore we can have the heterogeneous treatment effect to each one of these clients. So now João is going to talk about our results in production.
So we have results to show in production using our second method, the causal first, and we are able to have a reduction on churn when comparing the treatment and control group of 35%. When calculating the churn rate over the 6 months following that treatment. And as you can see in all of the periods, the churn rate is always higher in the control group when compared to the treatment group. For the later solution that Gabriel mentioned, we only have yet offline results. At the moment, the new model showed better results. What is the way that we evaluate these offline results? Using this cumulative uplift plot. So basically, we need to train a new model. We have the scores of that model. The scores here are the heterogeneous treatment effect. And we need to sort those clients. So we have a list of clients that were assigned to treatment and control in the past. And because we cannot change the past, we cannot say, okay, in the past we call Gabriel. We cannot change to what had happened in the past if we call João. So what we wanted to do, or what we could do, is to have a model that sorts those clients that we pick in the past in a better way. And this is what we evaluate here. Basically, we have a new model, we make the inference in the test set, then we sort those values based on score and create groups, in this case, deciles. And because we are doing the random trial control, we have both treatment and control in each one of the deciles. And we can calculate on all the clients that are in that group what is the churn rate in the clients that we have been treated and the churn rate over the clients that had in the control group. And our goal here is, if our model is good, the top 10%, the first decile should have this difference higher. So our goal here is to have a monotonic descending line, and we want to maximize the area under this curve. And because as I already mentioned, these offline results only tell us that we are sorting the clients in a better way, the clients we picked in the past. However, when we put this model in production, the model will pick different clients. So we need to do some kind of A/B testing to test this in production.
So,
and that's it.
That's it. Thank you.
Thank you so much, João and Gabriel. Feel free to just sit down. And we have a few questions from the audience actually coming in. So feel free to just choose whoever wants to answer them. The first question is, how do you differentiate your, by the way, we have more than one question about this. How do you differentiate those clusters of customers that you had in the second slide? Is it kind of rule-based? Do you do some sort of clustering? What is kind of the approach there?
Well, as João also mentioned in the presentation, in order to select the clients for our market campaigns, we are looking for those clients in which we believe that they have the biggest uplift. That is the difference between the fact that client is treated, the effect is more positive than the fact that nothing would happen if we didn't call them. So overall, what we do is we select the clients that we estimate the biggest impact. And therefore, we believe that those top clients, for example, the 5th percentile, are the clients that are the persuadable ones, that have the biggest uplift. So in the end, if we look at the sure things, they are probably close to zero. The lost causes, they are probably also close to zero in the heterogeneous treatment effect. And the do not disturb ones, they will probably have a negative effect. So in this case, we believe that the persuadable ones are, let's say, the only ones that have above zero estimates. So in the end, what we do is selecting the top uplift.
Okay. And another question would be, how do you handle big data in these solutions, so large data sets?
Well, I'm not sure if you are talking about like technological framework or modeling steps.
I think it would be kind of the combination of these several. So what kind
I can answer that.
Technical
basically, this is most of the times is not a big data, let's say, problem, because we can only train with the clients that we assign to treatment. So imagine we have a company with like 10 million clients, but we only call like 10,000 for each month. So the data set is quite small. And these type of problems at the moment are not, at least with this package that we are using, are not using Spark or something like that. So at the moment, this is not a problem for us, but could be. For some treatment, for example, if you want to have a prediction of, let's say, a feature in the application or in a mobile application, for example, it can be.
Also in a technological perspective, EconoML, that is the package that we used, it's only locally implemented. So we can, like João said, we cannot implement this with Spark, for example.
Okay, very nice. What are your biggest drivers of churn? I don't know if you also did that analysis, but the biggest drivers of churn that you identified, and does that even come up within kind of the modeling that you do?
Yeah, but most of the, let's say, the feature importance of the model, it's quite things that we expected, like the loyalty period, which is at Notch, for example, not at every company, I think, telco company, when you have changed your contract, you need to stay for a period of time. So, of course, when that period of time it's over, it's closing. Yeah, it is one of the most important features every time.
We can also observe some suddenly changes in the consumption behavior of the clients, and this could be also a churn indicator. Yeah.